Hey everyone. So you've seen those incredible images AI can create, right? You just type in a few words and bam. But here's the thing. There's a hidden cost, a huge cost. These things are incredibly power hungry. And that's exactly what we're talking about today. A fascinating paper that might just have the solution. So you've got this incredible, almost magical art. But then, on the flip side, you have the reality. Giant data centers, humming away, just burning through electricity to make it happen. It's a bit of a paradox, right? But what if? What if you could have all the amazing results without that insane energy bill? That's the big question. All right, so here's how we're going to break this down. First, we'll really dig into AI's power problem. Then we'll look at the two main ways these AI brains are built. After that, we get to the main event, the spiking diffusion model. We'll check out the results, and trust me, they're impressive. And then we'll talk about what this means for, the future of everything. Okay, let's jump right in. Look, the reason models like GPT-4 or all those image generators are so mind-blowingly good, it's kind of brute force. They're just throwing massive amounts of computational power at the problem. A whole lot of really, really intensive math. And that brings us to this quote from the paper, which just nails it. The human brain, the most sophisticated thing we know of, runs on about 20 watts. That's less than a dim light bulb. It's just unbelievably efficient. And that is the gold standard. That's what AI is chasing. So to really get why this new model is such a big deal, you got to understand the two main approaches to building neural networks. You can kind of think of it like an old school heavyweight champion going up against a brand new lightning-fast challenger. So on one side, you've got your traditional artificial neural networks, or ANNs. I love this analogy. They're like the big, loud, gas-guzzling muscle cars of the AI world. Yeah, they've got tons of power, but man, do they burn through fuel. And on the other side, spiking neural networks, SNNs. These are more like a sleek, brand new electric car, super, super efficient by design. Right now, ANNs are pretty much the standard. The way they work is by sending these continuous signals. Think of it like a volume knob that can be at any level. But to process all that, they have to do these really energy-intensive calculations called multiply accumulate operations, or MACs. It's basically nonstop, complex multiplication, and that's exactly where all that energy use comes from. The results are amazing for sure, but it comes at a cost. Now, SNNs, these are really cool because they're modeled after how our own brains work. Instead of a volume knob, think of it like a light switch. It's either on or off, a spike or no spike, a 1 or a 0. This means the math is way, way simpler. They just have to do accumulate operations, basically just addition. It's so much more efficient. The catch has always been that for really complex stuff like making images, the quality just wasn't there. It couldn't compete with the ANNs. Well, until now, that is. So that's the big question, right? How do you get that top-tier quality without the insane power bill? Well, say hello to the spiking diffusion model, or SDM. This is the breakthrough from the paper. It's the thing that finally seems to have cracked the code, giving us the best of both worlds. Okay, so how does it actually create an image? The whole process is kind of like a sculptor at work. You start with just a block of random noise, pure static. The model then takes that static and converts it into those simple on-off spikes that an SSN can understand. From there, a special part of the architecture, a spiking unit, starts to chip away at the noise, step by step, over time, revealing a clear pattern. And once that pattern is ready, a final decoder just translates those spikes into the image you see. But there's a really clever trick that makes this whole thing work so well. It's what the researchers call the temporal-wise spiking mechanism, or TSM. You see, most SNNs treat every step in the process as equally important. But with TSM, the network can actually pay more attention to the later steps of that denoising process. This lets it learn with a lot more nuance, and it's a huge reason why the image quality is so, so good. Okay, the theory sounds great. The architecture is smart. But the real question is, does it actually work? Let's look at the results and see if this thing really delivers. And yeah, it absolutely does. Just take a look at these images. These were made by the spiking diffusion model. They're sharp, they're detailed, they look fantastic. This is the proof that a brain-inspired, super-efficient SNN can finally hang with the big, power-hungry ANNs when it comes to quality. So the images look great, check. But what about the energy? Did we actually solve the power problem? Did they manage to find that perfect balance of high quality and low energy? All right, let's get into the numbers. This table tells the whole story. That FID score column is a measure of image quality, and lower is better. As you can see, their new spiking model, the SD-DPM, actually gets a better score than the traditional ANN. Now, look at the energy column. The ANN model clocks in at over 29 millijoules, and the spiking model, a measly 10.97. That's a massive difference. Yeah, do the math. That's a 62.5% drop in energy use. This isn't just a tiny tweak or a small improvement. It's a huge, huge leap forward. And remember, it's doing this while creating images that are even better. And this chart just drives the point home visually. I mean, look at that. It's not even close. That first bar is the old way. The second is the new way. That's the muscle car versus the EV, right there in front of you. So, what's the big takeaway here? What does all this mean for the future? Well, this is way more than just one new clever model. This could be a signpost for a whole new direction in AI research. And for any of you out there who are researchers or developers in this space, here are the key things to pull from this paper. First and foremost, spiking neural networks are now a totally viable option for high-end generative models. They're not just a novelty anymore. Second, that temporal-wise spiking mechanism, the TSM, is absolutely crucial. That's the innovation that really made this work. And finally, they also have this cool training-free method they call threshold guidance, which lets you boost quality even more after the fact. It's a game changer compared to older SNN models. But this isn't really about saving Google or Amazon some money on their power bill. The real revolution here, the big idea, is about taking this incredible AI power out of the giant data center. And that really leaves us with a final, huge question. What happens? What becomes possible when an AI this powerful, this creative, doesn't need to be tethered to a massive server farm? What can we build when it can run efficiently right on your phone, in your car, or on your laptop? That's the future this kind of research opens up. Pretty exciting stuff to think about. Thanks for tuning in.